talk. I'm Dave. I'm a data engineer at DataTorrent working on back-end engineering and applications engineering. I'm also a committer for Apache Apex. I think we've seen this slide a couple of times. I'm going to go over it. You all know what Apex is by this point. Right. So in this one, what we're trying to sort of demo is that Apex can be your platform runtime or the runtime engine. You can essentially read from multiple sources and write to multiple sinks and do real-time visualization and or write to your traditional databases, NoSQL stores, what have you. It could be dimensional data or non-dimensional data. This is how the ecosystem is structured. At the bottom infrastructure layer is Hadoop 2.x compliance with Yarn. Sorry. Then you have Apex Core, which is the performant engine that does these in-memory computations. And then you have the operator library, high-level API, and batch support on top of that. In addition to that, you could have application templates, which are essentially frequently used data transfer or data aggregation or data conversion patterns that we have templatized as Apex applications, and that are available for plug-and-play use. You can extend those templates to write your specific operators for depending on your business use case. On top of that, you have the real-time enterprise suite that DataTorrent offers. Now, the topic of this session is dimensional compute with Apache Apex, or dimensional compute in streaming systems as such, and high-level API, which is the second part of the topic. They are not related for the record, but I got only one speaking slot, so, that's how it works. All right, so let's take a sample, that people are using more often than not, which is AdTech dimensional compute. And so in this particular case, what we are doing is we're reading a bunch of data from Kafka. It could be a single Kafka broker. It could be multiple brokers. It could also be multiple Kafka distributions or multiple data centers on which Kafka is situated, essentially different clusters of Kafka. We're parsing all of that data through a Kafka input operator, then doing some filtering and enrichment on the parsed tuples, then passing it on to the dimensional aggregation component, which is highlighted in yellow here, which will take care of aggregating data based on certain dimensions and metrics, and views, and then send it across to a store, which has a query in, which is actually embedded in the store, but it would have looked bad, so I've shown it outside, and a result operator to enable real-time visualizations after it. There's another talk, more detail on this aspect of the scheme of things, so feel free to join that one as well. However, for now, so what you're doing at a high level in this particular use case, you're reading data from Kafka, parsing it into multiple tuples, running some filtering and enrichment on that, and then doing dimensional computation based on your own schema, aggregating those tuples. That'll generate aggregates. The store will re-aggregate things and also give interfaces for a visual dashboard that you can create in real time to query into the store and get results out of the store. All right. So before I dive a little deeper into how dimensional compute actually works, let me just touch base upon a few concepts around it. So here it goes, right? So in any dimensional model, you actually break down that model into metrics, the actual dimensions, a combination of the dimensions, then aggregations and time buckets. Now metrics are just pieces of information around which you want to collect some statistics about. For example, revenue is a metric. It's not really, metrics are measurable, quantifiable, so you can collect statistics around those things. Revenue or number of clicks in ad tech, or the amount of time a user spends on an average on a page. Things like these, which are measurable and quantifiable, are categorized under the metric category. Dimensions are the variables which impact the metrics, or due to which metrics are impacted. For example, the page on which you're viewing something could be a metric. The publisher who is hosting that ad, or on whose page you're going to serve that ad is publisher ID, could be a metric. The advertiser whose ad you're viewing could be a dimension. Sorry, the advertiser is also a dimension like a publisher. The campaign which you're running is a dimension. Combinations, basically a set of dimensions for which you could compute one or more metric is essentially a combination. For example, publisher cross advertiser cross time could be a combination of dimensions. Combinations are essentially subsets of dimensions. Aggregations are the function that you want to apply to compute that measure. It could be top n, it could be sum, standard deviation, any other custom scoring function or machine learning algorithm for scoring that you want to use go into this aggregations category. Time buckets are essentially the periods or intervals of time over which you want to run that aggregation. Typically, the operator that comes pre-packaged with 3 configurable modes: 1 minute bucket, 1 second bucket, 1 hour bucket, for more than 1 day bucket. But you could do 1 week or 1 hour. And now with windowed operator semantics, you actually have more enhanced support for session windows and event time windows, both fixed length and otherwise. All right. The example of this model could be, like I said, in ad tech, you want to aggregate over key dimensions for revenue metrics. That would be the use case. And the dimensions could be campaign ID, advertiser ID, and time. So you want to run your minute-level aggregations, day-level aggregations, hour-level aggregations, what have you. And the metrics in this case could be revenue, impression, and clicks. So, the amount of revenue that was generated, that the ad costed to display, which users clicked over what period of time, and how many ads were actually served. The aggregation functions in this particular case could be some arithmetic mean, etc. Combinations are, again, campaign cross time, advertiser, and then the corresponding metrics could be revenue and impression, or you could do the full thing of campaign, ad, time, with revenue, clicks, impressions. Now let's dig a little deeper into how this dimensional data looks. So you're reading from Kafka, you're just reading let's say a JSON record or Avro generic record. You parse it into your ad event, just a POJO, plain old Java object, and you set the fields, and then you pass it on to the next stages to do this dimensional compute, right? After this phase, however, once you try to do the dimensional compute, one single tuple which was ingested through your DAG kind of explodes into multiple things depending on the combinations that you set up here. What happens is I get a single ad event, and it's broken down by the metric function. Like you can see, this column has all sum, which is the aggregate function, and it may have different advertiser ID, it may have different set of metrics on it. The other guy could have a different time bucket, different function, so on and so forth. So all of those combinations start populating across the DAG, and that really leads to a memory explosion. So just running dimensional compute arbitrarily will most likely cause your streaming application to go down, because the footprint in memory of these things is pretty large, and it's directly proportional to the cardinality of the events or the dimensions that you're passing to it. So that's why you break it into different stages. One is obviously the memory footprint. The other one is you want to have a scalable implementation of your dimensional compute. And typically, each partition should at least handle 100,000 events. That's why we divide it into multiple stages. You have the pre-aggregation phase, then the unification phase, and the aggregation storage phase. Each of them have a specified set of tasks, and they cover shortcomings of the other stage. For example, the pre-aggregation phase, one of the main purposes of the pre-aggregation phase is to sort of collapse the dimensional aggregates by their uniqueness. So typically, for unique aggregates, dimensional compute tends to scale by reducing the number of events entering the system itself. Example, if you have n events flowing through the system, they typically translate to a number significantly lower than n in terms of your dimensional compute. To elaborate, what happens is if I have a time bucket of an hour and I receive 100,000 tuples for a single publisher, and if I'm just doing a dimensional compute on publisher cross time, then essentially all those metric values are going to get rolled up into a single row. Then I get a huge cardinality reduction, and thereby my memory footprint goes significantly down. The other way is to use partitioning to scale up the dimensional compute. Theoretically, if one partition can handle 500,000 events, then 8 should be able to handle 4 million events. And when you collapse them by the uniqueness of their cardinalities, then they could be a significantly lower number. I've just assumed 80,000 here, but that's essentially a factor of the collapsing cardinalities that you have in your application. Now, this phase, however, does not complete the scheme of things. You sort of stumble into the problem of incomplete aggregations, right? I may have aggregated a value of impressions for publisher ID or for publisher name, let's say Google, to be 1 million events over a minute's window. Now that window passes through, and the next window comes in and I get 500,000 events more. The ideal number I need at this point is 1.5 million because there was something that happened in the windows prior to this. However, once that data flows off, it goes off, and you cannot really recall it from the next operator. So to handle incomplete aggregations or partial aggregates, we have the unification phase, which sort of combines them into smaller, collapses unique aggregates coming from different partitions into one, and then passes it on to the next one. So the setup for pre-aggregation phase is pretty straightforward. We have dimensions computation operator for it that takes in a schema POJO. It looks kind of like this. So this is the JSON kind of structure that you need to specify on the operator as a property to enable dimensional compute for it. The values highlighted here are essentially the key values to enable dimensional compute. So the keys are basically dimensions with their respective data type. Time buckets are 1 day, 1 hour. You could set them to arbitrary numbers, but just from a bucketing perspective, I've set it to 1 day and 1 hour. And then you, in the values section, you could have the metrics over which you want to measure something. So the metric values I have in this case are impression, clicks, and revenue. And aggregators kind of specify the function, the aggregate function that you want to apply on them. In this particular case, it's sum. And then you could have a combination of dimensions, which are essentially campaign cross ad ID, creative campaign, publisher, ad order, campaign ID. And then you may want to specify some additional aggregations that are not generic enough, but only for this specific combination. So you could do that with this additional values parameter. The way this works under the hood is pretty simple. You take these combinations and you apply time buckets, each of the time bucket values for each of the metric values. For example, I pick the first combination, campaign cross ad ID. I will do a cross with the hourly buckets, and then I'll aggregate for impressions, clicks, and revenue. And when I come to this guy, publisher cross ad order cross campaign, I'll do the same with 1 day and 1 hour with the additional aggregation function of revenue. Here's just an example of the ad event that I used as a POJO. So you pass this guy a POJO with the schema, and it does the needful for you. Let's come to the unification phase now. The purpose of the unification phase is essentially to combine outputs. So this phase essentially combines the outputs of all the partitions that were previously aggregated in the pre-aggregation phase into a single stream, which can then be passed on to the next phase, which is the storage phase. Now, why do we really need to combine anything, right? The reason for combining something is to reduce the number of aggregations even further. This unification phase is sort of pretty close to combiner in your typical MapReduce paradigm in terms of a logical implementation. But in terms of real-world implementation, it's quite different. However, the purpose is to combine aggregations locally and reduce the memory footprint, thereby giving it a higher throughput. The other reason is aggregations produced by different partitions, which share the same key, maybe on different containers. So you have to combine them before they go to a persistent store, because at the other end of the store, you have a business user who does not want to receive erroneous responses when he queries it from an external entity. For example, if I send a query saying, what's the number of impressions in the last hour, I don't want a result that says 500,000 at one point because it goes to partition A, and 350 because it goes to partition B. I'd rather want to see all that output combined into one, which is 850K. The implementation is pretty straightforward. We have a unifier for that, the dimensions computation unifier, and you just need to pass it an input event and the aggregate event. And it does the rollup for you automatically. Let's take a quick look at the aggregation storage phase. Now, this is the last phase of the dimension computation breakout. The purpose of this phase is to persist aggregates. We persist aggregates to HDFS using HDHT. It's a custom implementation of the H file format from HBase. That's done as a part of a store that DataTorrent has written and open sourced eventually. The purpose of this phase, like I mentioned, is to just store the aggregates. Now, the implementation for this is the dimension store. The function of the store is twofold. One is for enabling visualization of in-stream events, and the other end is to basically facilitate re-aggregation, because all of your data could come sharded. All these partial aggregates could come sharded despite the unification phase from other ends, because the unifier in itself could be multiple instances or parallelized. Hence, you need a level of re-aggregation before someone can finally query that tuple at the end of it. So the store basically produces, in the visualization phase, allows you to visualize events over time. This is done by a pub/sub-based query in and query out operator that's integrated with the DataTorrent UI. And in the aggregation phase, you complete these partial aggregations by triggering an aggregate of aggregates. So this aggregation phase receives aggregate tuples from everywhere, and it adds to aggregate tuples to create one based on the same dimensional key that you had specified in one of the earlier stages. Now, you may say, why do we have the previous phases? Because dimension store is typically IO-intensive operation, may cause bottlenecks in your applications processing. And the previous phases kind of reduce the cardinality of events, so the store will always have lesser number of events to work with, thereby giving a better query response experience to the end user when he drops in something. There are several new variants of this implementation now. You can use managed state with Apex instead of HDHT, but it's a matter of preference. Managed state is backed by a local file system-based val, and then the secondary is HDFS for it. Just a glimpse of the visualization here. I have not gone into too much detail on visualization at this point. The simple reason being there's extensive talks later in the day for it, and Sasha's smiling. I recommend that talk to you guys. Okay, now I'm sort of pivoting to the high-level API. And this is a real pivot because they are not related at all. This is just a flavor of writing Apex applications in a different way. So if you would have done any of the previous talks, you may have noticed that we have this compositional API, which is sort of a lower level in the weeds API that really lets you go to how an operator is set up and connect things within it. Now, the high-level API is a more factory builder kind of an API, a pattern that's used more prominently with, let's say, Spark, which allows you to just act on transformations and actions rather than at an operator level, right? So here's a current example, right? This is with the compositional API. So you write an application that implements a streaming application. You override the populate DAG method, and you add a bunch of operators to it. This is the hello world of the big data space. Here we are just doing a word count input operator. It's going to read some stuff from a file, do a unique count on it, and flush all of that data to a console output operator, and then I'm just connecting a bunch of streams. So as you can see, this is kind of verbose. However, if you want to write custom operators, it makes sense to give you lower level control. That was the initial philosophy behind Apex. Now, as more and more adoption is happening for the higher level API with other engines, we have introduced a similar one that lets Python or any other business users to sort of act on transformations versus operators. The motivation for a high level API was that it's easier for beginners to start with, kind of intuitive because you're working at an action level. It's quite a fluent API, kind of closer to English semantics than writing a bunch of code. From our experiences, it has a relatively lower learning curve. You are working on transformation methods in one place versus interacting with the operator library. The operator API, while the high-level API has its advantages and motivations, the compositional/operator API provides flexibility in addition to ease of use that high-level API gives, also closer to the Beam semantics, and it's more intuitive for application developers and business analysts to work with. Just a simple example of a stream API of the stream implementation. So we have implemented a few functions like they've been done with some of the more popular versions of it. So there's map, flat map, filter, group by key, group by value, window. I see a few smiling faces there. Pretty similar to that. Again, you implement the streaming application, you do populate DAG, and instead of the old way of adding operators, you create a stream object from a stream factory. Then you say you want to read something from a folder, apply a flat map on it, and then do some window transformations in which you are accumulating fired panes, basically keeping state until pruned, and then doing a count by key before you sort of pump that out to a console out. After all of these transformations are done, you essentially take a stream, add a transformation. Every transformation will basically add an operator to it with a start and an end, or one or more operators to it. And then when you call populate DAG, that stream will essentially decompose into a DAG like it does before, and everything works the same as is. I think I covered this slide in the previous one. Sorry. So the Apex stream is an unbounded data set of type, of a templatized type that you want to. It's essentially a graph structure that will hold all the operators and connections between operators from input to the other to the output. And each transformation method is going to attach one or more operators to that graph structure, and you're going to only decompose it into a DAG at populate DAG. It's just a small example of that. And Q&A. All good? All right, guys. Thank you. Appreciate it. Yeah. Go on. Yeah. Yes.
Thanks.
Yeah.
So for the dimensional computation, you divide the stream into multiple partitions, and let's say each one you are computing like some max value.
Sure.
And I wanted to clarify one thing, so that at the unification phase, you find out what is the max value across the partition.
Right. So I may have like 10 partitions of dimensional compute that's doing max. Then I may have multiple levels of unifier or multiple instances of unifier. But then all of that gets routed to a store wherein you have to run the max again. So I may run at the first level when it's all individual dimensional compute operators. I may run max on, let's say, 1,000 tuples each, find the max out of those 1,000. But really, in a window, I may have 100,000 tuples, right?
But in that case, you will be limited by doing aggregation such as min, max, or sum, and then again complex aggregations like median or
right. But now
be limited.
The thing is, you iterated over that 1,000 and you found one. So what goes out of that is one to the unifier. The unifier may be reading data from 10 streams. So the unifier just has to aggregate over 10.
For those kind of.
Sorry?
So if you are computing median, for example, which median may not be super accurate.
No, but at the store, you run that function again. Right? Store does the aggregate of aggregates. So the motivation behind breaking this into different phases is that the first guy applies the function, reduces the uniqueness in addition to applying the function. Second guy combines all of these partial values, and despite that, you may have things like arithmetic mean or median. that cannot be done in a distributed way, you need all of the data, that can be done at the store. So reduce everything to the store.
Your unifier becomes super heavy.
Sorry?
Then your unifier becomes super heavy because...
Yeah, but unifiers can be cascaded and scaled up and down as need be.
Okay.
So yeah, you can.
So for the high-level API, what kind of control do you lose versus the old API?
No,
sorry, could you talk a little bit about what kind of control you might lose if using the high-level API?
Right. So the thing is, high-level API is still in sort of progress, and the motivation behind that is that there will be out-of-box methods that are exposed, like map, flat map, filter, some transformation methods. However, you may not want to use any of these out-of-the-box methods. You may want to enrich from 5 different data sets, depending on, let's say I go to one data set, I enrich something. Depending on that enriched value, I want to traverse other cyclomatic paths for that enrichment. And you may end up traversing that. Now you have to write a transformation like this yourself. So you will end up doing that. There will be nothing out of the box. Alternatively, instead of writing it in terms of a high-level API, you could write it in terms of a compositional API, like you do with a Java code. Take your existing Java code, put it in a operator template, and then just include that operator template.
Yeah, is the high-level API able to take Lambda functions though?
Yeah, it is. Yeah.